Okay, so now we're going to discuss actual waterside diagnostics. With a Bosch geothermal heat pump, such as we have here, this TA025, water is everything. Without the proper gallons per minute flowing through the coaxial heat exchanger and therefore into the ground heat exchanger, we will have no effective heat transfer. We will have no value. So what we've got to do, we've made sure that hopefully that we have the right electricity and we also have the right airflow. So the next thing is to check the waterside diagnostics. The last thing we want a technician to do is to connect a set of manifold gauges for refrigerant processes to this machine. It will be the very last thing, and we try to always prohibit that as much as we can. We can check pretty much everything we need to know with the waterside diagnostics. So the process that we'll do is I will use available tools, a pressure gauge as well as a knife blade, some people call it that, thermometer, typically digital, and I'm going to go to the pressure temperature ports, commonly referred to as PT or peach plugs ports, that are on the entering and leaving side of the coaxial heat exchanger inside the machine. They're on the outside of it, but it's connected to the coaxial in the machine. We'll energize the unit. Now we always want to check a geothermal heat pump whether after it's been running for approximately 10 to 15 minutes. The first thing that I would always do is energize it in the cooling cycle and let it run for a few minutes, even if I'm checking it in the winter. The reason for this is because in the refrigeration processes in the cooling cycle, the refrigerant that may have air and non-condensables in it hits the mechanical sieve dryer, bidirectional dryer, in the refrigerant circuit first, helping remove any condensables that might be in it. Now if I do have to check it in cooling, then I could energize it or change it from one mode to the other in the winter and check it in the heating cycle. In the heating cycle, the refrigerant will approach the operating metering device first instead of the dryer. So additionally, we want to check it in full load. Now this particular unit has a Ultratech Copeland compressor in it, which is capable of 67% first stage in heating or cooling and 100% in full stage, or Y1 and Y2. We'll always want to check the unit in the waterside diagnostics in full load. That means either jumping it out or calling for it and keeping it in Y2 mode. So in this particular case, what we'll do is set up all of our components and testing equipment, and we'll refer back to the product literature for this particular unit, and then we'll energize it, in this particular case, in the cooling cycle. Now, if I'm checking in the cooling cycle, I will be determining what we refer to as heat of rejection. That is the heat that is absorbed from the airflow into the refrigerant, transferred into the fluid. If it is an open loop system, this would be only water. If it is a closed loop system, horizontal or vertical, then the fluid would be a combination probably of antifreeze and water. So we'll have some variables involved with that. Now, if I'm checking the system in the winter and I want to determine the other side, that would be referred to as heat of absorption. Some people call it heat of extraction. In that particular case, we're absorbing the heat from the earth into the fluid, transferring it into the refrigerant, rejecting the heat into the airstream. So in this particular case, we'll be checking in cooling, therefore we're determining heat of rejection.
As mentioned earlier, we like to check the waterside diagnostics in the second stage of operation. We're currently operating in the second stage cooling, and a simple way to verify that the thermostat is calling for the correct mode of operation is to look at the LEDs on the ECM control board. There are LEDs outside each terminal designation, whether it be G for fan, Y1 for first stage, Y2 for second stage, and O for reversing valve operation. We can quickly look at the lights to determine the mode of operation. Now, just because the lights indicate that is the mode of operation it should be in, we always want to verify that we are in second stage mode of operation by checking the current draw on the compressor. In the second stage mode of operation, the current draw will be approximately 25% higher than it is in the first stage of operation. So once we've verified that we're in second stage of operation, we can continue with our waterside diagnostics. Okay, with the unit operating, the first thing we'll do is we'll remove the caps from the PT plugs, and we'll take an insertion type thermometer and we'll insert it into the PT ports once we've lubricated the stem on the thermometer and we'll take a temperature measurement of the water entering the coax and the water leaving the coax. Then we'll remove the thermometer, and we'll take our pressure gauge. We'll take the PT port adapter on the pressure gauge, and we'll also lubricate that. We'll take a pressure measurement entering the coax and a pressure measurement leaving the coax to get our pressure drop, or our delta P, to input it into our formula.
Okay, so what you've just seen is my counterpart Mark gathering data from the live machine. We're talking about a TAO25. We are operating it in cooling, so we're calculating heat of rejection. We want to make sure that any electric heaters are off, as well as any heat recovery package, commonly referred to as the superheater. All of these must be in the opposition. What Mark has found by taking the PT ports, or pressure temperature ports, on the coaxial entering and leaving, he has determined that the entering fluid temperature is 68 degrees. He's also determined that the leaving fluid temperature is 81. As we're talking about cooling, we're absorbing heat from the structure and rejecting it to the earth. So the temperature should be getting hotter when it leaves the coaxial. So here we have a delta T of approximately 13 degrees. That's one of the three factors we're looking for. Additionally, Mark had to gather the data with a digital psychrometer at the return. He had to determine the entering dry bulb temperature, which he found at 67, and the entering wet bulb temperature at approximately 60 degrees. Then he determined from the coaxial the entering fluid pressure and the leaving fluid pressure of 14 psi and 13 psi, so roughly he found a pressure drop, or delta P, of about 1 psig. So we take this information and we go to the current TAO25 full load data. On the middle of the right side of the page, you're going to find in the spec data fluid pressure drop. What appears closest in our data to 5.6 psi, or is 5.6 GPM at approximately 1 pound of pressure drop. Okay, remember earlier we focused on the formula used for calculating heat of rejection in the cooling cycle, and we said that that would be factors of delta T across the heat exchanger times the GPM times the brine factor. Now what we found, what Mark determined from the live equipment, was that he had approximately 13 degrees delta T, or temperature difference from leaving to entering across the delta T, rejecting heat to the earth. We determined from the product literature that 1 psig pressure drop was equivalent to about 5.6 gallons per minute. That's just what we need as one of the factors in our formula. He also substituted for the brine factor 500, which we said earlier was water only, and that's what we were using in this particular case. If Mark had been using a glycol, antifreeze, methanol, or any other acceptable antifreeze solution with a closed loop, then he would have simply substituted 485 into the formula. So now we have all the factors to give us the answer, or 13 degrees delta T times 5.6 gallons per minute times the brine factor of 500 for this TAO25 at these conditions to determine the heat of rejection into the earth. Now the final step in determining the heat of rejection in this particular case, remembering that we have a TAO25 and we're operating in the cooling mode, what we have calculated is approximately 36,400 BTUs per hour is being rejected based on our conditions at this particular location. Now we go to the specification data, which I referred to earlier, and down here on the lower right of the TAO25 page, in full load is capacity data, full load cooling. One of the columns is labeled heat of rejection, MBTUH, thousands of BTUs per hour. Now we're talking about cooling, so we'll use this as the data to compare what we found against. Now if we had been in the heating mode, heat of absorption, we'd simply go to the right over here. Same formula, same calculation methods. So in our particular case, he determined 36,400 was actually being absorbed and rejected from the house into the earth. And if I look at the data, what closely represents the conditions we were under, which fall under entering fluid temperature, entering air temperature, dry bulb and wet bulb, and entering GPM, or GPM flowing through the heat exchanger, I have determined from the specification data that we should be operating at close to 31,000 BTUs per hour of total heat rejection. So the way to determine how well this machine is running at these particular conditions is what we found, actual divided by specified. So actual at 36,400 divided by approximately 31,000 from the specs, and we come up with an answer of 1.17. We convert that to percentage by multiplying by 100%, and we are operating at approximately 117%. The Bosch criteria for cooling or heating is a minimum of operation of approximately 90% or better. So in this particular case, if a technician was in the field and checked it the way we have determined and shown you, this would be acceptable to Bosch and should be acceptable to you as well as the consumer. Whether we're operating in the cooling or heating cycle, the measurements and the calculations are the same. If we were below 90%, then we would have to think beyond the concept that maybe something is wrong with the water circuit or the air circuit or possibly the refrigerant circuit. The last thing we would want to do is put our gauges on this machine.